Great. Well, it's a pleasure to be here. As Naomi said, I've been around the world studying things and visiting. And people often ask me when I meet with them again, why do you practice in Champaign, Illinois? And my answer usually is that it's one of the few places in the world where most of my patients are smarter than me. And it is true. Well, today it is a little bit better, or maybe a little bit worse, because this lecture hall has witnessed some of the giants of physics lecture and whisper to the next generation of giants the most intimate secrets of Mother Nature. There's a language barrier. My son called me yesterday. He cannot be here. He's at the University of Chicago. He has exams next week. And he asked me, what are you going to talk about tomorrow? About medicine and surgery or about physics? And I said, what's the difference? So one of the problems that we run into, as this illustrates, is a problem of translation. We may be talking about the same phenomena, but perhaps in different languages. And if we can bring these languages closer together or provide some level of translation, we can achieve great things. So let's get started here. We are going to try to talk about physics of vision and blindness and vision again. Some of the recent therapeutic breakthroughs, new opportunities for benefiting patients, and future advances and emerging technologies. I'm going to try to give you a 5-minute introduction to the eye anatomy. So 5 minutes for anatomy, 5 minutes for physics. It's December 5th. In 5 days, on December 10th, there's a Nobel Prize awarding ceremony. So I'll talk about 5 eye conditions, 5 cures, maybe 5 great scientists. So 5 sets of 5s. If by the end of the lecture you remember 3 sets of 3, it's great. And if next year you remember one thing, that'd be fantastic. But you can always talk to me. All right, so here's our 5 structures we're going to be concerned with. This is the cornea, this is the lens. These are going to be bending, transparency and bending function. There's a retina, some kind of a receptor to get the light, and then collect it and then transmit it through a little cable called the optic nerve to the brain. And you can see the same thing there. I'm not going to play too much with this model now, but basically perhaps just to show you that this is how light goes back through the cornea, through the lens, and the lens is actually this little thing here that is transparent. Now, in terms of sight, definition of sight is pretty simple. You can just talk about light perception. If you perceive light, you have sight. That's most often not sufficient. We talk about 20/20 as so-called perfect vision. We can probably do a little bit better. And I may spend a little bit of time later on this. But you can have 20/40, 2200, etc. So when the denominator gets bigger, your vision is worse. And we may spend a little bit of extra time on that. So you can think of 20/20 or 6/6 as a ratio, and it's 1. And if this ratio of 1 gets to be a fraction, 0.5, etc., then it's not good. Legal blindness in the United States is 20/200, and that's 10 times worse than normal vision. Then we talk about count finger, hand motion, light perception, and no light perception. So here's a definition of blindness. The other definition of blindness, and I'll talk about this a little bit, is if your field of view is restricted. So 20 degrees of field. Your normal field is about for one eye, it's maybe 160, and there's some overlap between the two eyes. So roughly, if you say you feel it's 10 times worse than normal, then again, the World Health Organization definition of blindness is at 2400. So here's blindness, no light perception, 2200, 2400. But a picture is worth 1,000 words. And do you know the artist? Thank you. And do you know the artist? Okay. So that is also Pablo Picasso. So we need 5 things to see. We need transparency. We need to get light to focus where it needs to focus. And there are a couple of ways of doing this. The most common one is by bending it. So light comes sort of parallel. If it comes from a distant object, you need to bend it. And then you need to locate it on a detector called the retina. You need something to transmit it, and it has to go to the brain. Ultimately, it's the brain that sees. Okay? And I'll very briefly talk about some implants that go directly to the brain towards the end of the lecture. So you've heard about Maxwell's equations, maybe, Malus law, etc. So if you look in the dictionary under M, all of the laws of physics and such, you find Murphy's law. And Murphy's law of ophthalmology states that anything that can go wrong will. So transparency, sure, it will fail. And it will fail in multiple ways, and we'll talk about it. How about the bending of light? It fails in many, many different ways. And you can, if you wear glasses, take your glasses off, and you'll see what happened. You probably know. The detecting retina can have a number of problems we'll talk about, or it can come detached. Transmission can be affected, and the optic nerve or cable that transmits the signal to the brain can also fail. And the brain can also fail in a number of ways. And all of these failures, according to Murphy's law, can and will result in blindness. Okay? So here's a normal picture. This is from the National Institute of Health, NEI, National Eye Institute. Normal picture. This is if you are nearsighted. So if you have your little goodie bag, you can pull the pair of glasses that's in there. And if you have glasses of significant correction, you can just take them off and look at the world, and it should look something like that. It's always nice to look at the exit sign so that you know when to run, but it's a good test of your vision. Now, if you don't wear glasses, or you have your contacts on, put your glasses on and look at the exit sign and see what you're seeing. And it's kind of blurry. It can be blurry like this. Now, it can also be blurry to this point, and that's from a cataract, or it can get much worse than that as the cataract progresses. This is more or less what a diabetic patient with a diabetic retinopathy will see, and at some point they will cease to see completely as the blood fills the eye. Age-related macular degeneration is a very, very common disease, unfortunately, amongst the elderly, and it takes out the central part of the vision. The central macula is affected. So this is what they would see. If you pull your little card, there's a little card just like this one here, from your goodie bag, you can look through the top little oval and look around, and this is how someone with macular degeneration would see. Then you have one with diabetes, you have one with glaucoma, you have one with cataracts, and they are marked. So you can have that experience yourself. So here's glaucoma, and you can see it's sort of a little bit of the opposite of macular degeneration, because it's the peripheral vision that fails. This is retinitis pigmentosa. It's a genetic disease. It's actually a collection of genetic diseases. And again, it affects the periphery first, and then the central vision goes. Now, we talked about fields of vision. If you pull this little card that has a little plus sign and this big black circle, this is a little harder to do. What I'm showing you here is your field, your normal field of vision. This is a right eye, and this is the left eye. If you close your right eye and look straight ahead, you have a blind spot. So we are all blind in some way. Okay. There's a blind spot here, which anatomically corresponds to where the optic disc is. So this blind spot you can actually observe by closing one eye. Let's say you're closing your right eye. Extend this little picture in front of your left eye. Look directly at, I'm sorry, yeah. Put the black dot, the big black dot, to the left. So the left eye has a blind spot to the left, the right to the right. So you're closing your right eye, you're looking at the plus sign, and now you're seeing the plus sign, but also the black dot. Keep looking at the plus sign and slowly move the plus towards you. At some point, what will happen? It is so weird. All right, so if you succeed in doing the little experiment, and if you cannot do it right now, just do it at home. It works. Okay? Just make sure you close the one eye. Make sure the big black spot is on the side of the eye you're looking with. And look at the plus sign. Keep bringing it close very, very slowly. Okay? Don't go like this. Don't go like down. Just go straight. And slowly bring it in. The big black spot will completely disappear. Okay? You do have some blindness in you, no matter who you are. And if you don't, let me know. We'll run an interesting experiment. Okay, unfortunately, as disease progresses in certain conditions, that blind spot can become much more extensive. And this is unfortunately a patient who came to see me many years ago, and that's how the field of view looked. He did have glaucoma. I encouraged him to get treatment. He started and then he disappeared for a number of years. When he came back, he looked like this, disappeared for a number of years, and unfortunately, this is how he looks now. So treatment can maintain vision. This is a left brain stroke. The left brain looks to the right side of the world. The right brain looks at the left side of the world. This is, again, a patient of mine who had a stroke in the back of his head. And unfortunately, it took the whole right world out of his field of vision. And we will talk about some of these issues. Okay, so basically, you know, anything that can go wrong will, and it keep going wrong all the time. So this is your life. From 0 to 90, we talked about glaucoma. That's about the time when people get it, although everything you could get congenitally or very early in life, but most commonly you get it here. We talked about diabetic eye disease. We talked about cataracts, and we talked about age-related macular degeneration. The gradual red intensity increasing here corresponds to the worsening of the condition. And these percentages correspond to the number of people who basically go blind from the condition once they have it. So if you have a cataract and you do absolutely nothing about it, you are going to go blind. Now, I cannot tell you exactly when. You may die before you get it. You get the cataract. I mean, before you go blind from your cataract. But if you don't die, you will go blind. Okay. So that's kind of a little map of the blindness as life progresses. Now, what we have here is nearsightedness and farsightedness, which are very, very common, and you get it very, very early. That's why many of you have glasses on. That's why many of you have contacts on. That's what many of you should have glasses on. And we'll talk about these. So treatments, do we have treatments? Yes, the good news is that we have treatments for a number of these diseases. So refractive errors like the yopias, myopia, hyperopia, presbyopia, these are bending issues. You can do glasses, you can do contacts. So open your goodie bag, there is the glasses you already worked with. There's one little contact. If you've never seen a contact lens, you're not a contact lens wearer, go ahead and open it up. Okay, it's a little container. There's another very small one that I don't want you to open. It's like the flimsy one I want you to open now. It's very, very flimsy, and it's amazing optics. It's so nice, so light. It's amazing. You can put it on your eye and see. Okay, so open it up. It has a little bit of fluid in it. Do not drink it. You can pour it in your coffee cup if you're done, and then you can do other things that are supposedly more sophisticated than they are. You can do LASIK, and we'll talk about this in a second. Then we talked about cataracts. Well, you can just remove the cataract, and I'll show you some ways of doing this. Glaucoma, it's essentially inappropriately high pressure in the eye. You can reduce the pressure in a number of ways. There are some surgical procedures. The retina can play a number of tricks on you, swell, detach. There are some good treatments for these. And the brain, of course, you need a transplant if your brain is affected. Okay, so let's talk just maybe a few minutes about physics. Okay, I just want to, they won't pay me if I come here and I don't talk about some physics. They won't pay me. All right, so going to Chicago, very, very simple. I'm not going to do big time equation. You're not going to see an equation today. Well, maybe a small equation. Okay, here are a couple of equations. So simple physics. You go to Chicago about 120 miles, driving 60 miles an hour, takes you 2 hours. All right? So the distance is your speed times time. Now, you can also flip this around. The speed is distance divided by time, and the time is distance divided by speed. All right? So that's very simple algebra. Well, you can actually use all of these. So if you know any two of these quantities, you can get the third. So if you know the speed of something, and you know the time it takes to go from one place to the other, then you can find the distance. So if you drive your car for 2 hours, and it says 60 miles an hour, and after 2 hours you are in Chicago, then you know that the distance to Chicago is 2 times 60. It's very nice. All right. Same with inverting these things here. Now, I'm going to say something about the index of refraction that's very strange and weird. And if you don't understand it now, don't worry. We'll talk about it more later. So let's say the absolute speed limit is 60. You cannot go any faster. Okay? Otherwise, you get a ticket or you just break the law. And now let's say that you are in a place where you have to go 45 instead of 60. So that ratio is interesting. You know how much slower than your maximum speed you're going. And it's 60 over 45, and it's about 1.33. So that ratio is called the index of refraction. That would be your index of refraction as you drive. All right? This, of course, we're going to talk about when we talk about light. Light has a speed limit. There's a speed limit on light. It cannot go any faster. But light itself goes slower if it's in water. And light goes slower if it's in glass, and light goes slower if it's in anything else. So that degree of slowing is characterized by that number, which is the index of refraction. Now think about what you would do. Let's say if there was a highway that took you, that allowed you to go 60, you'd go 60. Now if there was a highway that allowed you only to go 45, you maybe would try to avoid it somehow. And if there was a bunch of different highways, 45, 35, 55, etc., then you would kind of finagle a path that would get you there as fast as you can. Right? And that path would bend your straight line driving to Chicago. All right? So think about this, and we'll talk about it some more. Now, we said that you can get the distances if you do this. Here's a beautiful example, again, of the cornea of the eye with an artificial lens that was implanted, and we'll talk about this in a minute. And this is ultrasound. It has beautiful anatomical resolution. And all you're using here really is this little formula where you're getting the distance. You're bouncing some ultrasound waves, and they come back, and you measure how long it took to get back to you. And based on that, you measure the distance to each one of these individual structures. And you get this beautiful picture that tells you a lot about the anatomy that we cannot actually see with light, because you cannot see here beyond here, and sometimes you cannot see here for a variety of reasons and so on. All right, so a little bit more about optics. This is from Professor Bahat Salah's book on photonics. And light, you can understand light in a number of ways. As ray optics, as wave optics, as electromagnetic optics, and then quantum optics. Now, for the eye and simple things like glasses and whatnot, you live about here in ray optics, and we're going to look at a couple of examples. Now, if you're going to use lasers and do surgery and stuff like that, and then you are in the world of quantum optics. And then if you use a number of diagnostic devices and to understand certain phenomena in the eye too, you're going to be somewhere between wave optics and electromagnetic optics. It's all the same optics. The real truth is here. But you don't need all of the complexity of the quantum optics world to understand that this laser is moving in a, well, not the laser, but the light is moving in a straight line, for example. Or that if you bounce it off a mirror, that it will reflect with equal angles. All right, so physics works. Now, there's this guy in Alexandria over 2,000 years ago. His name is Hero of Alexandria. He studied geometry. And in geometry, they told him that what is a straight line? It's the shortest path between 2 points. Okay, so a straight line is the shortest path between 2 points. So he learned that. Then he looked and observed that light goes in a straight line. So he concluded that light follows the path of shortest distance. Okay, what a profound observation. Well, it turns out that if you bounce, let's say you have a mirror. I don't have a mirror, but if you, well, I do have a mirror, maybe. Yeah, well, sort of. So if you bounce this light here, it comes out reflected with an equal angle on both sides of the perpendicular. Okay? So we see this. It turns out that this simple law of reflection, instead of saying the angle of incidence equal to the angle of refraction, you can just say that light follows the shortest path between the incoming point and the outgoing point. So to go from here to here, bouncing through the mirror, it could have done a number of things. It could have done this and then went around and around and around and then come back here. It could have gone here and then did a number of... It turns out that this path is the shortest path. Okay. When you put light through water, it doesn't go in a straight line. It bends. So that's not the shortest path. But remember, I told you something about the index of refraction and going to Chicago. I told you that light goes slower in water than it does in vacuum or air. So what is light doing? Well, light is extremely clever. Light takes the shortest time. It may bend, but it's bending because it wants to take a shortest path in this particular highway where the speed limit is only 45. And it turns out that most of the time, all of the time for practical purposes, light takes the fastest route. It may not take the shortest route, but it takes the fastest route. And simply based on this one principle, you can understand tons of optics, lots of optics. And surprisingly, for those of you who are in physics, there are many other things you can understand based on that so-called principle of least action. You can define some quantity that is somehow minimized in some of the most complex theories in physics. But I'm not going to talk about that. So a bunch of very smart people, such as Fermat and this should be Snell and Descartes, told us how light reflects and how it bends and whatnot with different formulations. But this simple formulation is very simple, very elegant, very beautiful. It works all the time. Okay, so other things about light. So here's this very smart guy. Around the 10th or 11th century, he was the first one to tell us about the correct explanation of vision. Everybody thought that the way you see is by emitting light out of your eyes. So I'm here. In order to see you, I have to go like this. You know, there's some beam coming out of my eye. Well, of course, we know that's no longer true. And that was one of the first people to identify that. We'll talk about the camera oscura and so on, and the theory of refraction. So let me skip this. Okay, so how can you get this light to get to your retina? Well, the simplest thing to do, you'd think, is bend it around or whatnot. Well, it turns out there's an even simpler way, which is to do this little camera oscura or pinhole. So I want you to take your glasses one more time, put them on, look at the exit sign. It's really nice to look at the exit sign. You always know where you can run. And then take this little square with a little hole in the middle. Okay. Close one eye. Okay. And look at the exit sign and put the little pinhole in front of your eye that sees. And tell me what you see. So first the glasses, close one eye, look at the exit sign, make sure it's blurry. If the exit sign is clear while you're wearing the glasses, let me know. I'll book you out for an appointment. Okay, so look at the exit sign. It's very blurry. Now put the little pinhole in front of it and tell me what you see. It's perfect. It's weird. Okay, so what's happening? I mean, you don't need a lens, no glasses, no LASIK, no nothing. All right? I should start selling these. These are glasses with little pinholes. All you have to do is look, put pinhole everywhere. You'll never miss one. And you can see. Well, it turns out that that's all you need. I mean, here's the tip of the arrow. If it goes through a little pinhole, then you get that upper tip of the arrow. If the bottom of the arrow goes through the pinhole, you get the bottom. The picture is inverted. Okay, it's a good picture. All right? It's a really good picture. And you can make it really good. Now, if the whole, really what this does is that for each little point of light, it gives you something about the projected side of the pinhole on the screen. All right, now if you make the pinhole too big, then too much light is going through, and you have blobs and blobs and blobs and blobs and blobs, and the arrow is a bunch of big blobs, and you get something like this. Now, if you make the pinhole too small, then you run into something else called diffraction. I haven't talked about yet. Okay, I will mention it in a minute. But light comes into the pinhole and kind of collides. It's too narrow for it, okay? And it spreads out. And that's not good because it gives you a blob or something equivalent, and you get something like this. Too big of a pinhole, too small of a pinhole, better, better, better. That's probably the optimal right here. And loose is, what? What does loose mean? Does anybody know? Spanish? Light, light. Okay. So this was, again, from a UNESCO project, and this is taken from Hecht Optics book. All right, so these guys developed this nice laws of bending, and does this work? How can we turn this on? You want to turn it on for me, Erica, please? Yeah, please turn it. So these guys just give kind of clean, computationally useful ways of telling us how light bends. Because the pinhole, what's the problem with the pinhole?
Not enough light.
Not enough light, absolutely. Okay, you're trying to get little light so it doesn't give you blobs, but then you end up with not enough light. Now, the other problem with a pinhole is what? You're like a what? Like a glaucoma, advanced glaucoma type person, because you've lost your peripheral field, right? It's beautiful. You can see the exit sign, but that's the only thing you can see. You can't see the good lecture going on, right? All right. So this is just some examples of, can we dim the lights just a little bit? So we're not going to do pinhole. We're going to bend the light, okay? So we want a lot of light. So let's get a lot of light and bend it. And these two guys told us how to do it, or what the laws are. It's the same law as Fermat and the same law as the minimum time, but it's computationally more friendly. So you can write a computer program to do this. And you can see the light is coming from here and bending and focusing right there. Now, this gentleman won the Nobel Prize in 1911 for doing this kind of things on the eye. Basically, he told us all of the structures and all of the curvatures. So one thing to understand also is that if light comes on a flat, let's say you have water on this side, which you do, and light comes straight like this. So you go from a high-speed place to a low-speed place, but you're coming straight on, it's not going to bend. But if you're coming here, now there's an angle, and there is a difference in speed limits. So you have an index of refraction that's different, so light is going to bend. So you need two things. You need a difference in the indices of refraction, okay, or difference in speed of light. So an index of refraction is not the same as the other side. And you need some kind of an angle between the light and the surface that you're crossing. So this is usually, you want to conserve this so you don't get all kinds of crazy light. So you need to have a certain level of curvature. So you need curvature from an optics of the eye point of view. You need a certain curvature, and you need an index of refraction change between the two. So this gentleman, again, won the Nobel Prize for his work on the dioptrics of the eye. And Don Barnhart and I, Don is from eyesight. I don't know, is Don here? No, he's not here. He called me this morning. Worked on some kind of a model that you can play on the computer with Mathematica and the like, and do this kind of thing. Okay, so pinhole we talked about. Now, what else can you say about light? Well, it's not just a bunch of little particles. It's also a wave. Now, you guys came to 5 lectures before this lecture, so I don't need to tell you what you already learned. You know there's a quiz at the end of this lecture, right? So this is... So the question at some point, and Newton was one of the people who was very interested and had his views about this, is the light a bunch of little balls that are emitted that we now call photons, or is a bunch of waves? All right, and it turns out that it's both, you know the answer. And because it's waves, then you can get interference effects. So you have one, let's see, E1 is a dotted one here, E2, and then they are going up and down at the same time. They're in phase here, so they add up, and you have a big wave. Now, if you put them in opposition, when one goes up, the other one is going down, this one here is going down, then they cancel out, and you get this. Now, if the two are of equal amplitude, they'll cancel out completely. You'll see nothing. All right? And this is the kind of phenomena you can see. And you can get these ripple effects where you have a very, very dark or very bright intensity here and then nothing here, bright. You get these kind of fringes. Or now, the nice thing about this is that light has a wavelength, and we'll talk about this. And these can be controlled by manipulating the wavelength. What I'm trying to say is that you can see changes here by changing very small things, like small distances, for example, of the order of the wavelength. And the wavelength is something very, very small. All right? The wavelength is something very small. I'm going to tell you how small it is. And because it's so small, you can use this kind of effect to measure structures, biological structures, that are on the order of that wavelength, let's say. And I'll say more about it. But you can look at very, very small things within the eye and other biological structures. So here is the so-called electromagnetic spectrum. Light is an electromagnetic wave. There are lots of things that are electromagnetic waves, X-rays, gamma rays, radio waves, microwave, etc. The optical region is somewhere here, and what you see is right here. Now, you thought you were important, right? So that's all you see. It's really a pretty small fraction of the whole spectrum, but it's a very important fraction. This is now blown up to show the optical, and still, here is the visible. And these are in the ranges we're talking about are things like maybe 400 to 750 nanometers, so half a micron or so. So very, very small structures. Okay, very quickly about lasers, because we're going to do laser physics. This is all I'm going to say about quantum optics. You can pump electrons to a high level, and then they kind of decay by what's called stimulated emission, and you get a coordinated emission of light that is very powerful, very useful. You can get laser pointers and other things. Now, this guy you saw before, and he's sticking his tongue. You saw that before. What you maybe did not see before, you did not know that he is sticking his tongue out to this guy. So Goldstrand was a very, very smart guy, a very smart ophthalmologist, did a lot, won a Nobel Prize. But he spent a lot of his time, maybe a decade or more, trying to prevent Einstein from getting the Nobel Prize. And you know that Einstein did not get a Nobel Prize for the theory of relativity, which he wrote maybe in 1905. When did Einstein get a Nobel Prize, you know? Yeah, 23, 21, or something like that, 1920-something. And one of the reasons, apparently, there are not many reasons, but one of the reasons is that this guy was writing, trying to disprove the theory of relativity and preventing Einstein from getting the Nobel Prize. Now, Einstein is responsible for our theoretical understanding of that portion of lasers and whatnot, although he was not very fond of quantum mechanics. Okay, so the eye power, let's go back to the eye. There is a cornea that has 40 power and the lens that has about 20 power, for a total of 60. What is this power business? We can bend parallel light with 1 diopter to 1 meter, 2 diopters, bend it to half a meter, 5 diopters, bend it to 1/5 of a meter. Now, the eye is about an inch long, so you want to bend it much more than that. And so you need about 60 diopters for this reason mainly, to bend the light into the retina. Okay? Now, if you have glasses with 1 diopter that you don't need, or you need glasses and you don't wear them, this is how you see the world. 2 diopters is here and 3 diopters is there. The glasses I gave you are generally about 3 diopters, so it blurs your vision to this degree unless you need them. Bending, you should bend here. If your eye abnormally bend in front, you're myopic. If it bends less, you're hyperopic, right in the back there. So you run into this kind of problems. And how can you fix it? Well, it's very simple. You can put a lens that unbends if you have too much bending, or a lens that bends if you have too much bending. So you can give this nice lady some nice glasses, and she seems to be reasonably happy. She has half a smile. Okay. Now, the other thing you can do is you have a cornea that has a certain curvature here, and based on this curvature, it bends the light to a certain degree. Now, you can change this curvature. So if you are bending too much, if you make the cornea flatter, it will bend less, and the light is going to go there. Now, how can you do this? Well, just buy yourself, this is a human hair, buy yourself an excimer laser. Okay. When people see this, they say, oh my God, it's like so, it does such a nice job, it's so fine here. Can you believe this is a human hair? In fact, it took so many shots to get this. Okay, a human hair, you can measure it at home if you want, is, I don't know, like maybe 40 microns, 50 microns, 100 microns, depends whose hair it is and where you got it from and so on. But it's like many, many microns. Now, the excimer laser will get out 1/4 of a micron at a time. So it takes maybe hundreds of shots to get this. So you can do this to the cornea with the laser light, meaning photo. You can change the refraction or the bending, refractive, of the cornea, chara, and remove it, shave it, tectomy, get it out, exit sign. Exo-ectomy means you get it out. So you get photorefractive keratectomy, or PRK, which was FDA approved in the United States in 1995 and was available before that other place in the world. So all you're doing is you're basically sculpting the cornea to change its curvature. All right? Then came LASIK, which is a minor modification to PRK. And interestingly enough, do you know what laser stands for? Laser is light amplification by stimulated emission of radiation. We talked about it. We talked about Einstein. Well, that's called an acronym, right? Now, LASIK is also an acronym for laser in situ keratomylosis, which means sculpting the cornea. So it's an acronym made with another acronym. All right. So now you can take this nice lady and give her that laser thing, and she is maybe a little happier. I don't know. Is she happier? Maybe. All right. So that's your banding story. Let's go back to our transparency story. Very simple. Here's this is not very transparent. It's called a cataract. Not transparent at all. This person is going to have horrible vision. Actually, these are some of my patients. And this person is going to have horrible vision. Okay, not very nice. Now, a lot of these patients have a lot of problem. The point is that there's huge, the main cause of blindness in the world is cataracts. Okay? Maybe 2/3 of blindness in the world is from cataracts. And it's curable. I'll show you how. And actually, this Arvind Eye Hospital is one of the most efficient places to cure blindness in the world. Okay? And I may talk about it if we have some more time. So what can you do? They have some help here from technicians who measure pressure and whatnot. And sometimes the cataract is even black, like that. So how can you take a cataract out? Well, let me show you a very nice technique. So the problem is your lens is supposed to be transparent like this, and then it becomes like that, okay? And I'm going to put it right in here. And I'm going to tell you a very nice technique to take it out. So how do you take it out? Well, you take your nice little surgical instrument, this one, in your bag, and you go make a very small incision, and you go like, see, it's not working. Every time you try to show someone something, it doesn't work. Erica knows all about it. And you do this. See, you don't have the right instrument. Yeah, here we go. And you do that. Wonderful. This technique has been used for thousands of years. And you know what? It works. It does work. It's not a very good technique, but it does work. This technique is called couching. It comes from French coucher, because you lay the lens down. So if anybody comes with an instrument towards you and says, "Voulez-vous coucher avec moi ce soir?" the answer is non, merci. So I am going to show you something a little bit better, okay? If we can get, let's see if I can get this to work. She showed me how to do it. Here's some more modern techniques.
Sam
Let's watch
Barrett
that.
of Perth, Australia, produced this video more than 5 years ago. It's entitled The Evolution of Lens Design, and I would say that Dr. Barrett was way ahead of his time.
And this was done before some of you were born, actually, but it's still very modern in a number of ways.
Hello, Dr. Barrett.
Well, I'm pleased you made your appointment because I wanted to discuss your operation with you. What I plan to do is to remove the cataract and replace the cataract with an intraocular lens or an implant.
Will it take long?
No time at all.
That's good. I've got a game of space golf planned this afternoon.
Well, you're lucky you weren't born 2,000 years ago. Come across to the time dealer. I'll show you what I mean. The history of cataract extraction extends 1,000 years before the Common Era, when couching, or simply dislocating the cataractus lens posteriorly, was the common method employed. The Roman writer Celsus in De Medicina gave a detailed account of the operation using a single sharp instrument. Still now, don't move.
The 18th century heralded a new era of innovation when Jacques Daviel described an extracapsular method of surgery, which was followed by intracapsular surgery in the same century and phacoemulsification in the 20th century.
Monsieur Daviel, your patient is ready. Yes, yes, yes. Mon Dieu, bring him now.
In extracapsular surgery, the nucleus is expressed leaving behind the cortex and capsule. Whereas in intracapsular surgery, the entire lens is extracted within its capsule. Phacoemulsification uses ultrasonic energy to fragment or emulsify the nucleus of a lens, and therefore allows the entire lens to be removed through a 3mm incision. This method was introduced in 1967 and became increasingly popular in the following decades. The concept of replacing the cataractus lens predates the reduction to practice by several centuries. Casanova, in his memoirs, relates that an Italian oculist, Tedini, discussed the idea of implanting an artificial lens after a cataract extraction in 1764. The first successful intraocular lenses were implanted in the posterior chamber in 1949 by Harold Ridley. Choice further developed anterior chamber implants, which were initially introduced by Strempelli in 1953.
You have one of these lenses in your bag. It's in a little plastic container. It's extremely small and extremely delicate, so you can look at it if you want now or later, it's up to you.
In 1975, Pierce returned to the posterior chamber with a rigid tripod implant, and in 1977, Shearing introduced a posterior chamber IOL with compressible loop haptics. Smaller optic single-piece PMMA IOLs were introduced and enjoyed a period of popularity in the 1980s. Foldable implants composed of silicone, hydrogel, and acrylic materials became available, and finally surgeons were able to achieve the full benefit of small incision cataract surgery made feasible by phacoemulsification.
There's now a much nicer way of putting these in with an injector. Okay, so we do this with an injector now, not with forceps.
To avoid early
so it's like
capsulotomy.
An injection source. And you can go through 1.8 millimeters.
A new hydrogel implant designed to avoid this limitation was introduced. The lens is manufactured as a single-piece construction, late cut, and milled from polyhydroxy ethyl methacrylate with a water content of 38% when hydrated. This process, followed by tumble polishing, achieves a precision and quality which is not
Does anybody know what the music is?
Of manufacture.
I can go home now. You guys are so much smarter than I am.
Which merges via a concentric flange into a terminal loop with a total diameter of 12 millimeters. The loops are far more flexible than conventional implants, but are sufficiently rigid to support the lens in aqueous within the capsular bag. Furthermore, the fact that the lens conforms to the capsular bag is considered more physiological than existing designs. Conventional posterior chamber implants with polypropylene loops, extruded PMMA loops, and one-piece PMMA lens designs all deform the capsular bag. The capsular bag becomes oval and the loops extend into the ciliary sulcus. The new hydrogel lens was specifically designed for modern surgical techniques comprising phacoemulsification and small incision surgery. a 3.5 to 4 millimeter incision is made in 3 planes extending into the cornea.
So again, the incisions today are about half
The capsula rexus,
or
which is the
1/3
preferred capsulotomy for this lens
as
design, is
large
then
as what's
performed.
shown here.
Hydrodissection between the capsule and cortex, and then between the nucleus and cortex, delineates the lens into its epinuclear and nuclear components. Endolenticular
Fast forward just a little bit here. It goes pretty fast, actually. So again, that's the
easier and
implementation,
safer
the
than that
implantation of the
required
lens.
with 3-piece flexible implants.
Anybody feels a little dizzy or something?
Saying, Mr. Ventura, you're lucky you weren't born in the past. We've come a long way since then.
So what sort of lens will you be using in my operation?
This is the implant I'll be using.
Oh, the flexible lens first used in the 1990s.
Right, you've got it. The child of evolution is perfection.
All right. So let's see. Can we switch back?
Thank you, Dr.
All right.
Barrett.
So we are going.
Our
to
next category
start
is funniest.
this. Here we go. So, a very exciting question, but it's how do you compute the power of the intraocular lens you put in? And there's like decades of making errors, and it's amazing how people never learn. One of the great persons who really gave a solution to this was Dr. Fyodorov from Russia, and the article was written in Russian originally, and it took many years to translate it, and even after it was translated, nobody seemed to pay attention. So people were making all kinds of mistakes, putting the wrong... Now, unfortunately, Dr. Fyodorov passed away in a helicopter crash, but his daughter, Dr. Fyodorova, is an ophthalmologist. I met her April 2008 in Chicago, and I asked her, I told her, Dr. Fyodorova, I'm really honored to meet you. And she said, I'm honored to meet you too. And I said, do you practice in Moscow? And she said, yes, I practice in Moscow. Where do you practice? I said, well, I practice in Champaign. And she said, oh, I love Champaign. So we may invite her for next year's lecture. Okay, let me move on here. We want to go to the back of the eye. If you, what physicians do is that they write these 3 letters, W and L. They check your lungs, your heart, your head, whatever, and W and L. So W and L stands for within normal limits. Now, when we have lazy residents or medical students, we tell them, what does WNL mean? WNL means we never looked. Okay, so the problem with we looked at the front of the eye, glasses, LASIK, cataract. Problem is that if you try to look inside someone's eye to see the back of the eye, you can't see anything. All right? Now, how can you look at the back? The problem is that you have this whole thing as if you had put these glasses I gave you and 10 more of the same. And then you look at the exit sign. You're not going to see anything. This is in the way. So forever, people could not at all see the back of the eye until, of course, the patient was dead. And then you can open it up. So this very smart guy, Jean-Marie, wrote this article, presented to the French Academy. And basically, this is what he did. So to see the retina of a living animal, he submerged the cat. It's true. This is true. I'm not making it up. And he published it, in a reputable place. So he took the cat, he submerged the cat. So this did two things. It scared the hell out of the cat. So the cat's pupils dilated. Okay, this is sort of a epinephrine, kind of. And then, so the nice pupil dilation. And then the water canceled out, at least partially, the bending effect of the cornea. Right? Remember the speed of. Turns out that the cornea and the water are very close in index of refraction. So on your highway, the highway that the light takes to travel, okay, it's very close. It doesn't have to bend anymore. Okay, so that facilitates the visualization of the retina. Now, notice that this was about 100 years after we had the first microscope, the first telescopes. So people not only understood optics, but they built instruments. And yet, this is what we got 100 years later. Luckily, this gentleman, von Helmholtz, came in 1850, another 150 years later, and built an instrument to look at the retina. And he wrote to his dad. Any high school students in the audience? It was so obvious, requiring, moreover, no knowledge beyond the optics I learned in high school. 1850. And it's true. It had to wait 150 years past the 100 years that Mary had. Von Helmholtz did many, many things. I will not have time to go through. But one of the very interesting things that to know is that Michelson, of Michelson-Morley fame, who measured the speed of light and thought it would be different if you go from one direction to the other, because they were trying to figure out what ether does and whatnot, and kept being disappointed that he kept the same speed of light no matter which direction. The first time this experiment was done in von Helmholtz's laboratory in Berlin. And this basically was one of the major pillars of the theory of relativity. Okay, so 150 years, every 150 years we get the clever idea, a little slow. So here's the retina, normal. It can be diseased. Can have blood. We have spectacular treatments now for macular degeneration. Okay, it's amazing. Again, for thousands of years, nothing. And actually, as recently as a few years ago, we had nothing. Now we have something. I'm not going to go into it. This is a patient with a retinal detachment that I saw last month. And the field of vision was starting to disappear. And I repaired this. The field came back. Ramon y Cajal won the Nobel Prize in 1906 for figuring out what the retina is made of. Well, it turns out you have several structures in the retina, and we can map them now with a technique called optical coherence tomography. It does use two principles. One is of the light coming back and bouncing back, and the other principle is the principle of interference of light waves. And then you can get an exquisite detailed picture of the structure of the retina and treat disease accordingly. So here are some future surprises. Okay, in 5 days, going to be the ceremony for the Nobel 2009. This year, it's awarded in physics for fiber optic and CCD. Okay, couple charge devices like what you have in your digital camera and like. So I'm going to show you very quickly a little clip. Can we get the clip? Of how these techniques help us every day in getting patients to see. I'm sorry. Erica is wondering how come I cannot use the computer. Yeah, this one, yeah. So all that is a view of the retina. Now this is in surgery, okay, and one light, fiber optic, is illuminating the retina, and the other one, fiber, is guiding the laser that's putting laser inside the retina. Okay, very brief. That's what we have here. And this is based on this kind of technologies that are receiving the Physics Nobel today. I wouldn't be able to show you this if we didn't have this other one. All right, so let's close this. This is a lecture in 3 days by Willard Boyle, one of the recipients of the Nobel Prize. This is Argus Panoptis from the Well, he's talking about an extension of man's vision. I'm going to show you that in a second. From Greek mythology, he had hundreds, some people say millions of eyes all over his body. And there is an implant, a retinal implant called Argus 2, which is a device like a CCD that you can implant for totally blind patients who have never seen before. Okay? I'm going to show you how it looks. This is a device implanted. This is a new one, Argus 2. The other one has 16 electrodes. This one has 64. It's not much compared to the millions we have. However, it does take someone who is totally blind to a seeing person, and there's future in it. Can I see the other movie, please? I'm going to show you a very brief movie, and I'll stop in about 5 minutes, just as a fair warning.
A unique collaboration exists between the public and private sectors, led by the Department of Energy. Its purpose is to build the most advanced high-density microelectronic tissue interface, one that enables cells to communicate to machines. This advanced technological platform allows the ability to interface with cells and is applicable to all sorts of other future technologies, such as environmental sensors for cleanup, to counter bioterrorism, and to harness energy. The testbed chosen to prove out the capabilities of this approach is the retina, because it is a well-studied neural tissue.
This pigment here
Moreover,
is the pigment
the retinal
of retinitis
approach allows us to develop a cure for millions by restoring sight to those for whom there is no foreseeable cure. Age-related macular degeneration, or AMD, and retinitis pigmentosa, RP, are blinding diseases that destroy the light-sensing photoreceptor cells in the eye, but leave the remaining visual system relatively intact. The success of this project is based on collaboration and technology transfer. Progress towards the first goal was achieved with an initial prototype. The patient wears a special pair of glasses, which contains a tiny camera, which transmits an image to the implant, which is then transmitted to the remaining healthy retinal cells, optic nerve, and brain. This is how the patient is able to perceive light. The second generation of artificial retinas have provided useful visual percepts with an acceptable safety profile. They're smaller, more powerful, and have been implanted with less surgical invasion. The consortium of 5 national labs, 4 universities, and 1 commercial company share technology via a cooperative research and development agreement by tapping into the Department of Energy laboratories and their resources. It produces unparalleled engineering advances not capable in a serial research environment. The results have been astonishing, but we hope to use this knowledge to venture into other disciplines, such as in devices to treat Parkinson's disease, cochlear implants, and insulin pumps. It is through a unique interdisciplinary consortium that leverages the expertise within the national labs, academia, and industry that our group has accomplished the development of an advanced technological platform, the artificial retina. But it is clear that this is just the tip of the iceberg, just the beginning of spawning a whole new genre of high-density, abiotic-biotic interfaces.
All right, a lot of these technologies are really related to a lot of the work that's being done here at the University of Illinois. So I definitely encourage you, I need 1 more minute to finish up, but I do encourage you to talk to the physics people here. They are very smart, and this is the place to be if you want to study these exciting technologies. So here is grandma again playing basketball after her implant. She was totally blind before. And this is kind of the projected future for this implant. Finally, here's my summary. Blindness is too common and unacceptable. It's curable in many cases. We need to make it totally curable in all cases. Physics is absolutely key. Awareness of need in the US and in the world. Just do it. Your grandmother is standing there, waiting. Don't have her wait for 150 years. Thank you for your attention.
Any questions for Dr. Sayegh? Fascinating.
Absolutely true. This goes to this whole concept of, the question is, people who have LASIK surgery, if later on they develop cataracts and you try to do the cataract and put a lens in, the calculation of the lens implant is trickier, okay? So there are bad news and good news. So first of all, we are doing very well in terms of straight cataract surgery. You can tell exactly what the implant is. Now, it's very interesting that it's apparently simple optics problem, like the one of what implant to calculate and to implant, is giving us so much trouble. It turns out that the problem is being settled. It's one of my areas of expertise, and the reason, there are a couple of reasons why. The main reason of why we had this problem is that people used fudge factors. So basically, I say, okay, it's 2.3 on average. Now, it's an average for a normal cornea of normal curvature, etc. Now, after LASIK, the cornea flattens a lot by, 10%, 15% of its original value, 20% of its original value. So the fudge factors that were fudged when you were working on eyes that had not had LASIK surgery are no longer valid. Okay? And people were just using the same fudge factors. So when I mentioned Dr. Fyodorov, the interesting thing is that in the work of Dr. Fyodorov's work, it was a paper by Fyodorov, Kolinko, and Kolinko. It's pure optics. So it really should work all the time. For some reason, the next generation of formulas that were proposed were fudge formulas, where people did average. They took 100 patients, put lens, and okay, I'm going to adjust the curve like this. The factor alpha is like 2.78. This is very crazy because you already had the fundamental optics, and now you're doing fudging. So it says something about the history of science, the history of medicine. There's something to learn from this. And we're going back to so-called theoretical fundamental optics formula. Yeah. But yeah, so if you've had LASIK, the interesting thing is that nearsighted people develop their cataracts earlier too. And the economic issue is that a lot of people don't get their LASIK until they're somewhat older, because when they're younger, they don't have money to pay for it. So the time between your LASIK surgery and your cataract surgery is not as long as some people would think. So, oh yeah, at 20, I'm going to have LASIK, and then when I turn 70, I'm going to have cataract. It's really not like this in the real world. So people may come to have LASIK around, I don't know, 48, and then because they are nearsighted, they get their cataract a little earlier, so maybe at 58, let's say. And so it's just 10 years. And LASIK has been around for that long. Yeah. Go ahead.
If you are nearsighted and are wearing contacts and glasses for years, is it recommended, like in the future, to get LASIK surgery, or is it just
So the question is, I've been wearing contact lenses for many years. Is it recommended that I get LASIK? Okay, I don't recommend to people. I don't go around telling people, here, I recommend you have LASIK, I recommend you have LASIK, and whatnot. LASIK is an option, okay? So you have to be a candidate. Most people who are reasonably healthy, with reasonably healthy eyes, other than their nearsightedness, will be candidates. You have to be 18. Your vision has to be stable. If it changes every 2 months, you don't want to be lasering a moving target, right? But if all of this is satisfied, then you would be a candidate for LASIK. LASIK is a surgery, so there's some level of risk, but obviously if the risk was very significant, we would never do it. Okay, so the benefits really are enormous, and the risk is very, very acceptable. So it's something you could consider, and it's essentially a permanent solution to to the problem of nearsightedness. We have 15-year follow-up studies that show that it's very stable. We don't have 50 years follow-up studies, but it doesn't look like it's going anywhere for most. Now, there are some people who should have never been lasered that were. So some people were like minus 20 nearsightedness, which is huge, crazy, pathological. And people are still doing these lasers on. So these people are not doing well. But now, over many years of experience, we know what the window is. And for people who are much higher in nearsightedness, we have other solutions. So, yeah.
I know people who have had cataract removal, and as a result, they suffer from double vision. What is the cause of that?
Okay, so the question is, some people who have had cataract removal are suffering from double vision. Okay, double vision is a very entertaining topic. But very briefly, there are two kinds of double vision. There's what we call monocular double vision and binocular double vision. So if you cover one eye and you still see double, then the problem is in the cornea, in the optics of that eye. The cornea, in the lens, the lens may be tilted. There may be some kind of irregularity in the cornea, etc. Okay, if you cover one eye and you see perfectly fine, just one of everything, cover the other eye, see one of everything, okay? And now you open both eyes and see two, then it's a different problem. It's from alignments of the eyes, okay? So one question, of course, is how come we don't see two of everything, right? We have two eyes. Why don't we see double all the time? This is a very hard question. I have to come back here year after year to try to answer it. Okay? But in practice, we know we don't. So when there is a misalignment, and often this will happen concurrently in the age group that has cataracts. So for example, let's say you're 70 years old and you're having your cataract surgery. Most likely, not most likely, but many people also have high blood pressure. Well, it turns out that people with high blood pressure, people with diabetes sometimes, may develop double vision because of issues of blood supply to the structures that control the eye movements, etc. So the eyes are not as well aligned. And then they may say, oh, I just had my cataract surgery, now I see double. Now, if they saw double like the day after, then probably it's related. And the first question to answer, is it like monocular or is it binocular? So send them to me. We'll take care of them. Any other question? Okay, I want to thank you for coming in on such a beautiful day. And again, you're the next generation of physicists.